This video demonstrates the use of the Add Shield Walls tool. There are several ways this can be done. We will look at two of them. This software will help the PCB designer quickly and easily add the features to the PCB design that will enable the board to be used in an RF chassis with shield walls that either protrude through slots or cutouts in the PCB or that sit on the surface of the PCB. Here's an example of an RF board and the metal chassis that it's mounted in. There are cavities milled down into the metal. The cavities and walls between them help to isolate the different RF signals from each other and from the rest of the system outside the chassis. Here's a picture of just the chassis by itself. You can see the pockets that have been milled into the metal to provide clearance for the board and the components and conductors on the bottom side of the board. And here's an image of a board that will have a shield chassis part mounted on top of it. The chassis will not go through the board. This kind of shield has an EMI gasket material dispensed in paste form into channels in the bottom of the shield walls that hardens somewhat to provide a permanent seal. Now as to how the software works. First we'll look at the mode of creating cutouts or slots in the board for the kind of chassis walls that will go through the board. The basic idea is that the designer will draw simple lines and circles on any user layer, and the software will convert those objects into the features needed to define the cutouts. In the case of internal cutouts, the software will add contours or milling paths, which the PCB fabrication shop will use to make the actual holes or cuts in the board. It will also add a solder mask clearance and routing keep out around the cutouts to keep solder mask and conductors from getting too close to the edges of the cutouts. When the cutout crosses the board outline and route border will be modified to include the cutout area. No contours will be added in this case because the board outline will define the shape. Because mechanical designers will often want to specify a minimum radius for all the inside corners of the metal chassis, there is a feature in this tool to add bends to a polyline with sharp corners. The designer can just draw straight lines, combine them into a polyline, and then add bends to the corners with this function. Generally, lines will be drawn to define walls, and circles will be used to define the location of mounting bosses for threaded holes used to secure a cover or lid onto the chassis. The lines and circles can be of any thickness and size, as the software will use all of the provided parameters to draw the actual features. It is also important to note that the software contains an algorithm which combines all the shapes into a single continuous shape for each cutout, with a radius added anywhere there is a sharp corner junction. The size of this radius is controlled by the smoothing factor value. Here's an example of making a cutout that crosses the board outline. First, the desired lines and circles are selected, and the Add Walls Using Selected Objects button is pressed. After the function is complete, we see that the board outline and the route border have been modified to encompass the cutout area. The software also creates a loop on the solder mask layer around the board edge to define a solder mask clearance. Now let's look at making an internal cutout. We select a group of lines and circles on a user layer and set the parameters. In this case, I set the cutout method radio button at the top of the window and then set the wall thickness. Then we execute the Add Walls function. Because one of the features added to the board is a contour mill path, the software needs to know what size tool to use for the contour. A small window will appear with a drop-down list of all the drill and mill tools available in your library. Select the tool size you want to use for the contour, then press the OK button. The contour, routing keep out, and solder mask clearance objects are then added to the board. We can then go on to select other lines and circles to make more cutouts. When the Add Walls function is executed another time, the drop-down list in the Select Drill Size window will default to the last tool selected. The contour, routing keep out, and solder mask objects are added again. Looking at the image of the chassis and board again, we see that there are openings in the walls where different parts of the PCB are connected to each other. We will call these openings gates. When the unit is fully assembled, there will be a small machine metal part that slips down into the gate openings and makes contact with the PCB to create a complete EMI shield. When drawing the walls using simple user layer lines, it is easier to draw them without the gates at first. This is mostly because the gates will be a specific size, and it would be difficult to know exactly where to start and end the drawn lines. The software includes a gate removal function to subtract the gates from the walls based on the size of the gates. The PCB designer will most likely work with a mechanical engineer to determine the size of the gate part. This information can then be used to set the gate size parameters in this tool. Let's do an example of a gate removal. The gate location is determined by the location of a circle and a line segment. The circle is only used to enable the designer to easily specify the gate location. It can be placed anywhere near the line and does not have to be directly on the line. The software will do the math to project the circle's location onto the nearest point on the line. The designer does not have to be very precise in placing the gate if its location is not critical. Of course, if there is a need to precisely locate the gate, more care can be taken to place the circle at the desired location. When the gate removal function is executed, the line is split into two separate segments and trimmed back by the correct amount so that the gate will fit exactly between the line segments. In this case, I have drawn the lines at the desired wall thickness to illustrate how the gate will fit. I'm going to move a gate part in my PCB design from another location and place it in the new gate opening to show how it fits. I pick up the gate part, move it, and rotate it. Now I'm going to draw a line I'll use to place the gate part. I turn on the snap function in Xpedition, then draw the line from the end of one of the wall lines to the end of the other one. The center point of this new line will be used to snap the gate part into place. We can now see that the gate and the wall lines fit together nicely. We want a small clearance in there for manufacturing tolerances, but in practice the actual metal part will fit snugly into the gate opening. I'll delete the construction circle and line, leaving us with just the wall lines and the gate in its new location. Now let's look at the other method of making shield walls, where the shield sits on the surface of the PCB. With this method, the software will add a conductive shape tied to a chassis ground net on the PCB and a solder mask clearance for the same area, but will not add contours or route keepouts. Here's an example of a board with this kind of shield. We have already drawn the shield walls using user layer lines, and some mounting hole bosses have been added with circles. Again, the size of the circles does not matter. They will be added to the board based on the parametric value of the screw mount boss diameter. When we execute the add walls function, it may take some time to process everything. There's a lot of math going on behind the scenes. When the processing is complete, I will turn on the route layers and the conductive shape on the top layer will be visible. Now I'll turn on the solder mask layer and we can see that a solder mask clearance has been added in the same area as the conductive shape. We also have to add a shield wall around the board outline. However, because there may be several iterations of making the internal shield walls as the design progresses, it's best to leave this part until the end. The conductive shapes for the internal walls take this into account, with a smooth transition being made in the area where the internal walls will meet the board outline walls. The internal walls can be drawn, deleted, and redrawn again, and no matter where they intersect the board outline wall, there will always be a smooth radius to connect the two. When the board outline wall is added at the end, it will overlay the wall shield areas without any sharp corners or discontinuities. Before adding the board outline shield wall, we need to select any circles for mounting hole bosses that are near the board outline. This will include them in the board outline wall shape and ensure smooth transitions between the bosses and the nearby walls. The board outline wall shapes are added to the board. We see that the internal shield areas, mounting hole bosses, and board outline shield areas all flow together smoothly. The different shapes can be combined if desired or edited in other ways to fit around other objects on the PCB. Take note that any traces going across the shield wall will be cleared so that they do not short circuit with the chassis ground conductive shapes.